So you were asked to graph these in college algebra. And when you graph them, do you remember finding this point? Do you remember finding this point right here? Yeah, that vertex. And if it opened down, I mean, it really didn't matter. It either opened up or down. That thing, we called it the vertex. Yeah, I was going to ask you how you learned it. So let's kind of take a vote and see if anyone remembers. Does anyone remember what we called this point? It was called the vertex, but it had an x and a y coordinate. We didn't call it xy. We called it something else. HK. Do y'all remember that? HK? HK? That was just a fancy notation. It's really just an x and a y coordinate. But on a parabola, we call it HK. And that had something to do, you don't need to write this down, but that had something to do with there was another form of quadratic functions that looked like this, which we call the standard form. And when we're in standard form, we can see the vertex. We can just look at it and see the vertex. But just throw that out, who cares? This is HK, all right? So to find the vertex, that depended on your instructor and how much they stressed. So can anybody remember how you would find the vertex of a quadratic if someone gives it to you like this? I'm just trying to see if people remember. Yeah, what's that? Yeah, something like that. There was a formula for it. And then the other hard way is to do completing of the square. You could like take this and complete the square, which was nasty. But there was a formula, and the formula said, hey, look, to find this point, right, the x coordinate, which we're calling h, is just going to be negative b over 2a. Now, does that ring a bell? Negative b over 2a. That's it, right? Yes? That was given to you. And nobody ever asked why, right? Nobody ever asked why. So let me see if I can convince you why it's that. All right? It's not going to, no, this is cool. This is cool stuff. Watch. What can you tell me about this vertex? From the calculus perspective, what can you tell me about the tangent line at the vertex? The slope is 0. Do you agree? So if I come here, or it doesn't matter if it opens up or down, whatever this x coordinate is, right? Whatever it is, whatever this x coordinate is, I know that the slope of the tangent line should be 0 there, right? So how I could frame that in mathematical language would be this. I need to find the x such that f prime of x is 0, right? This is telling you, hey, go tell me where the slope of the tangent line is 0. Remember, this function has a derivative, doesn't it? And that derivative graphs the tangents, the values of the tangents. I want to know where that graph of that thing is 0. So let's do it. Let's actually do it. You ready? It's going to look bad, but it's actually not going to be that bad. First, let's just figure out what's the derivative of a general quadratic function. What is the derivative of this? It's the limit, as h goes to 0, of f of x plus h minus f of x all over h, right? That's what it is. You agree? Which is the limit as h goes to 0. Plug x plus h in here and here. And we would get a times x plus h squared plus b times x plus h plus c. Do you all agree with that? That's x plus h into the function. Please do not confuse this h with this h. They're totally different, all right? Totally different. Minus, what am I going to subtract? F of x, which is that function up there. So I subtract each term. I'm not going to write the parentheses. I'm actually going to distribute right now as I write it. That would be the minus distributed, right? All this over h. I would now need to expand this and distribute an a, and then distribute a b, right? And do that right here. This is the limit as h goes to 0 of, let's see, ax squared plus 2axh plus ah squared. So I did this in my head. I expanded that out. That was x squared plus 2xh plus h squared. Then I distributed an a through to each of those terms. Then I distribute a b through. Plus bx plus bh. Still have plus c. Minus ax squared minus bx minus c. All of this over h. Are y'all still on board or not? Yes? It's all going away, right? We're getting good stuff here. C's are gone. Bx is gone. Ax squared is gone. Everything else has an h, right? So let me see if I can do the next line without too much work. I see that everything else that's there has an h. I'm going to factor the h now. I'm going to do h. It's going to be 2ax plus ah plus b. I believe that's it. All over h. I had 3 terms left. I had this one, and this one. They all had an h in it, so I pulled one factor of h out. That way I could do my canceling right now. And now I let h go to 0. And when that happens, this vanishes to nothing, and I get what? 2ax plus b. This, everyone, is the derivative of the function, right? The derivative of a general quadratic function is this, right? And what did we say we wanted to find? H, but what did I write down in words? I need to find what value of x, right? Where the derivative was 0. Where the derivative was 0. Here's your derivative. I want to know when that's my slope of my tangent line, right? I want to know when it's 0. So take that and set that equal to 0 and solve for x. So what would happen? You move the b over, negative b, and then you divide out 2a on both sides. And you get x is negative b over 2a. And there it is. That's your formula. If you want to find the x coordinate where your slope of your tangent line will be 0, then you must make your x coordinate negative b over 2a. And that is it. Cool, right? That's the way mathematicians work. That's the way we think. We want to do things in general. We don't want to do things over and over and over a million times. We say, look, if we have this, we can come up with a way of finding that vertex pretty easily if we just come up with a general formula. Now look, think about this now. What if you had, instead of a general quadratic function, what if you had a general cubic function? Right? Think about this now. We know that cubic functions look like, they can do this, right? You can even have them just do, you could have them do something like that, right? Any other thing? That was supposed to flatten out a little more. Let me do this one. You could just have this. Now, of course, you could flip it. This side could go up and this side could go down, or this one like that, or this one like that. Okay, so you could have one of those 3 pictures. You're either going to have the function go up, turn back down, go back up, or it's going to go up, flatten out and go up, or it's just going to go up and keep going up. One of those 3. But let's think about why it has to look like that. In college algebra, when you're graphing these, you were never asked to try and find that, were you? You were just asked to graph, but you were never able to determine how high or how low that thing went, right? We kind of just waved our hands at it. We said, wait till later, maybe. Okay, later is now. So the idea here is this. If we were to find the derivative of this function, right? if we just take that derivative and do what with it? We would be able to find where those happen. What did we just do? We had a quadratic function. I took the derivative and I said, hey, where's that derivative? 0, right? Same thing would happen here. If I take this function and I take its derivative, I would just set its derivative equal to 0 and solve. And that should give me where these things happen, right? Now, if we follow what I've said in class with what happens, if you start with a third degree polynomial, you take its derivative, it should be what? Second degree, right? We started with a quadratic, its derivative was linear. So if I take the derivative of this, I should get what type of function? Quadratic. How many solutions can you have with a quadratic function? 2 or 1 or none. All quadratic functions have either 2 solutions, 1 solution, or no solutions. As long as we're talking about real numbers. If you bring the complex numbers in, that's something else. So look, this is the case where you have 2 solutions. This is the case where you have 1. Look, the slope of the tangent line there is 0. And this is the case where you would have none. So, all right, we're getting ahead of ourselves, but I'm trying to get you to see that the derivative is a function, and that function is really important to us because we can really analyze functions now. We can take any function now, anything, doesn't matter what it looks like. It needs to be a function, okay? It has to still pass the vertical line test. And if we have a graph, we can go after all these points now. As long as we can take the derivative and set it to 0. If we can do that, we have a chance of finding where those points occur. And that's an important thing because, if this is your company and this is the time and this is the profit, let's say the money you're bringing in, and you're sitting there and you're going, well, obviously this is where we had the lowest profit, right? That's where we had the lowest profit. We would like to know where that happened, right? We would like to know when that happened, and we go and we say, remember that date? It's when we hired Nathan. Right? And then look, it's come up since then. Good job, Nathan. You thought I was saying that, okay, no, I meant it's better now. Yeah. Right? But you could talk about things like the growth of your profit, like right here, somewhere in here, I would have the I would have like the steepest growth, right? So I could say, what was going on about this time that we were having a lot, like an increase in profit, but the most increase, right? Because before this, our slope is not as steep. After this, our slope isn't as steep. So this is like the steepest place it happens. Understand? We want to know that information. This also works for, you're talking about something like an engine, right? And you have the pistons that are moving, and you're measuring the force coming out, right? The torque at the wheels, like what's that torque? You're measuring it all, and you're saying, where are we getting the most torque, right? Where's that most torque happening? Where is that happening? What was the position of everything when that happened? Well, you need to know how to find that point. Well, you just take the derivative and you set it to 0, and you'll be able to recover that point. So it's an important, you just have to trust me, it's an important skill. Yes, and there's another thing we have to look at also, because so when we get to it, it'll be set it to 0, but there will also be something else we do, because you could have a function that looks like this. You have a cusp, right? But this is definitely the highest point on the graph, but the derivative doesn't exist. So not only will we be looking at where's the derivative 0, we will be looking at where does the derivative not exist. That's going to be an interesting point that we have to analyze also. But setting to 0 is definitely in there. All right, let me go to the notes. How are we doing on time here?
We got like about
25 minutes. Okay, we already tried to connect. If you look at my lecture notes on this, I go through here and I try and connect the picture. There's the derivative, and I'm drawing it as I go. and maybe this will make more sense now. You know, the slope of the tangent line here represents, it's a negative value, so the derivative is negative. I go backwards, where was the slope? 0? Right up there, right? So the green function is the derivative. And more of the same. All right, we also have some notation now, some changes in notation. There were two fathers of calculus. I say fathers because they were both men. Newton and Leibniz. All right, Isaac Newton and Gottfried Leibniz were the two men who didn't discover calculus. They created calculus out of the need to get around this 0 over 0 thing. And the interesting thing is that they did it at the same time, the same period in time, in different locations of the world without knowledge of each other. So it's kind of like, what are the odds of that happening at the same point in time? But so they realized that later when they published, and like, oh wow, we were thinking the same thing. However, Leibniz doesn't get as much credit as Newton, because Newton also did laws of motion, and you know, he had a lot more on his resume compared to Leibniz. But they were both brilliant, and because they did things different, you know, because they did things on their own, they came up with their own notations for derivatives. And so when we say f prime of x, we know we mean the limit, right, and all that stuff. But there's another notation. You could just say, okay, y prime. So if someone gives you the function like y equals x squared minus 3x, there's the problem on the quiz, but write y instead of f of x. Then if you want to know the derivative, you can just write y prime. And everyone understands, hey, take the derivative. So do the limit. Prime means derivative, yes. And Leibniz would have written this instead. And you might ask yourself, why would Leibniz write that? Well, here was Leibniz's idea. Leibniz says, look, I'm trying to find the slope of the tangent line there, right? He did grab another point like this, and he did grab that point and start to move it closer to this point, just like Newton did, right? Move that point over. But if we just freeze the picture right there and draw a little right triangle, this is delta y over delta x. Delta meaning what? Change. So rise over run is delta y over delta x. If I let this delta get small, in other words, if I move this point really close, won't that delta x be infinitesimally small? And the delta y will be infinitesimally small? If I put them right on top of each other, right? I've got to make it real tiny. This is Leibniz's way of saying really tiny. Instead of using the delta, he wrote dy dx. And the d stood for like what we call a differential. It's an infinitesimally small increment. So that's his notation. But it means the same thing. Take the derivative. All right? There's also other notations that you may see. This one not so much. This one is just saying, hey, look, take the derivative with respect to x, meaning that x is your variable. Of what? Of this function. All right, take the derivative, treat x as your variable of this function. You could also have capital D in front of the function. That would also mean take the derivative. And you could have capital D with the subscript x in front of the function, which would also mean take the derivative. This one, we won't use it all in here, but if you ever take Cal 3, we will use that a lot because you'll have functions that have more than one variable in them, like x, y, and z, and you'll have to take what are called partial derivatives, and so the notation gets messy. If you just stick with primes, it all falls apart, so you need a better notation. So this is kind of for later on in calculus. We're really going to stick with these first three and sometimes this one. All right? I'm going to stick with these three and maybe sometimes this. Like, I'll show you another way I could have written this right here, okay? I could write this like that. And that would mean take the derivative of that. All right? I could write this, d dx, x squared minus 3x. That would mean, hey, take the derivative, treating x as your variable, of this. These are the same. Understand? All right. If you have a function, f, I just said that we could take the derivative, right? Take derivative. And what does it spit out? F prime, right? A new function. Right? So you start with the function, you take its derivative, it gives you a new function. So what if I ask you now take the derivative again? You could do that, right? Because now you just kind of erase the fact that that came from something. You say, hey, I have a function, take its derivative. This second application of the derivative would get you what we call the second derivative, and we would notate it with f double prime. 2 primes. And hey, that's a function, right? Take the derivative again. 3, right? And then at some point it gets ridiculous, right? You're not going to have like 18 dashes, right? 18 prime marks. So right about this point in time, we say, all right, let's just start putting like a number up there. But we will put it in parentheses. We're not just going to write f with a 4, we're going to do f parentheses 4. The reason why we do the parentheses is so you don't confuse it with this. This would mean take the function f, this one way back here, and raise it to the 4th power. Understand the difference? There's a huge difference between taking that and raising it to the 4th power and taking its derivative 4 times. Totally different answers, right? And how many derivatives can you take? I mean, you should be able to, well, theoretically, you can just keep differentiating, but as we'll see, sometimes eventually it goes to 0 or it gets worse as we go.
If someone wanted us to take like the second derivative, we would just say f.
They would give you this.
Double prime or something
Yes.
like that.
So here's f of x. Let me say I give you that. There's the original quiz problem, right? And I'd say something like find f double prime of x. So you'd have to take derivative once. After you do that, you take derivative again. So you have to do the limit twice here.
We take the shortcut in that.
We won't start doing second derivatives, third derivatives until we do the shortcuts. Okay? Because it's too time intensive to sit there and do limit over and over and over. So right now we're just trying to get you to see that if you start with a function, take its derivative, and it is a function, then you could do it again, right? You could do it again, 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 again. It's just an idea. Yes?
But doesn't it lose its power each time?
Okay, yes if it's a polynomial.
Okay.
But if it's not a polynomial, then things can get, what happens? We will look. Sometimes it gets nice, sometimes it's ugly, it just depends. Do you understand the question, everyone? If we start with like a quadratic, take its derivative, it's linear, right? Take the derivative of a linear function, it's going to be a constant function. And if we take derivative of that, it's going to be 0. And then it would be everything after that would be 0, 0, 0. But that's only with polynomials. All right, we already talked about differentiability as far as there's corners and cusps and things like that. So corners, breaks in the graph, vertical tangents. There was a very famous question in mathematics for a long time. And I need to go back up to this theorem, which I just went right past, sorry. Where is it? There it is. Theorem, right here. Differentiability implies continuity. So I want to talk a little bit about this statement before we actually get into the nuts and bolts of it. Look at this word implies that you see in math. Sometimes you'll see it as a double arrow like this. All right? Let me explain what this double arrow means. If, let's say I write this, if x equals 2, then x squared equals 4. Do you agree with this statement? Yes. If x is 2, then when you square it, you get 4. So I could write this instead of this. I could write x equals 2 implies that x squared is 4. That's proper mathematical notation. If this is true, then this is true. Implications do not work the other way around in general. Y'all agreed with me that that's true, right? Can I switch the order of this and it stay true? Can I write it backwards? If x squared is 4, then x is 2. It would be plus or minus 2, right? So this is not in general true, is it? Implications cannot be switched just because you want to switch them. So when you see a theorem and they say that this implies this, you have to read it strictly that way. You cannot reverse it. Another example I like to give that's a little easier to understand is the idea of like people living in the United States. If, let's say you're from Texas. So if you're from Texas, you're a legal Texas citizen. If you're a legal Texas citizen, then you are a US citizen. Do you agree?
Yes.
Yes? Does that work the other way around? If you're a US citizen, then you must be from Texas. No, that does not switch. The implication cannot switch. So that arrow right there isn't just fun, okay, fun notation. It means something. Now, if you ever see a double arrow, that means you can go both ways with it, all right? The implication works both ways. And you may have also seen this before. Have you ever seen this in a math book or something before? IFF? No? That means if and only if. This is also the equivalent of that double arrow. It means the statement they say goes both ways. All right. The dots, oh, that's therefore. Therefore. Okay, there's a bunch of different notation for math. All right, we won't get into that. Let me get back to this theorem. Let's get back to this theorem. This theorem says differentiability implies continuity. In other words, if you're differentiable at a point, then what? Then you must be continuous at that point. It does not work the other way around, though. If you say you're continuous, that does not mean you have to be differentiable. And I can give you an example very easily of a function that is continuous but not differentiable. And that would be that function. Or I could do the absolute value function, which goes this way, right? Do you agree that these are continuous? I can draw them without picking up my pencil.
Yeah.
But there is a point, a single point, where the function is not differentiable. Everywhere else it is, but that point it's not. So we could not say that this function is differentiable everywhere, right? It's almost differentiable everywhere. It's just got one problem, right? One place where we have an issue. So here's the question that mathematicians asked for a long time and they couldn't get an answer. It took a while to get it. They said, is it possible to have a function that you can draw without picking up your pencil? So it's continuous. But nowhere can you take the derivative. That it's nowhere differentiable. Do you understand the question? No? What do you think, sir? Yes? No? Maybe? Any idea what it looks like? I thought you were dreaming it up there for us. No? I mean, no one's going to come up with it in here, okay? Nobody is. It's not going to happen, all right? But let's think about it like the idea of it. It seems like we could make problems happen at corners, right? Anywhere we would have a corner, we need a corner everywhere. So what about this? Imagine this. Would that be a continuous function? That's continuous. Is it differentiable everywhere? Well, there's some problems here, here, right? I want this thing to be nowhere differentiable. I don't want to be able to take a derivative anywhere. Squish it together? Yeah, you can't do a vertical line because then it won't be a function. And then it needs to be continuous, so how about this? Look at this as like, have you ever seen shark teeth? Like shark teeth? Okay, if you look and you zoom in on a shark tooth, it's serrated, isn't it? So like on each edge of the tooth, there's additional little jagged edges like that. So imagine, that's what it is, and it's that way the whole way, right? So now I've got more discontinuities, right? More places where I fail to be differentiable. And then imagine zooming in on each one of those, and each one of those has its own little shark tooth and that they're everywhere. Can you imagine a function that looks like that? It's like sawtooth, but zoom in, each sawtooth is a sawtooth and a sawtooth and a sawtooth and a sawtooth forever. So it's like this infinite vibration as you draw this. Does that make sense? That's the concept. And a mathematician named Weierstrass was the one who came up with it. And let me show you what the function, I'll write the function down on the board. It's an infinite summation. Hold on. No, sorry. Cosine of b to the n times 2 pi. I believe that's it. I might be off a little bit, but anyway, it's an infinite summation. If you've seen summations, it's an infinite sum of cosine functions. So just imagine like a cosine function plus a cosine function plus a cosine function forever, which to you right now may seem like that's crazy. You can't have functions that go forever, but take Cal 2, you'll realize that we need them. They're everywhere. So it's not a far-fetched idea to have an infinite sum of functions. And when you take this function and you graph it, oh, where's my graph? There it is. Now, I can't get the computer to do a good version of it, all right? I've tried, but the computer gives up at some point, and it tries, but there it is. It's almost a cosine function, but within each cosine function, there's another vibration of cosine functions. And if you keep zooming in and peeling in, you just keep on seeing vibrations forever. And so if you try to go to a point, a single point, you're guaranteed to be at a corner. And anyway, so that stumped a lot of people for a long time. What's the use of the function? It's probably not a very useful function, but it exists, okay? And that's what mathematicians like to do. They like to answer weird questions.
So like somebody just sat down and thought about this for a really long time.
Yes. Yes. You know, it's weird. It's weird because
Is that like bragging rights at that point? Probably like that's what they do it for.
no. Look, as a pure math, I was a pure math major, which means that you can do different branches of math. Okay, you can do like math education. You can do applied math, where you go and do, I don't know, go build bombs and whatever. There's applied. There's different things. Pure math is really just trying to answer questions that haven't been answered. Okay, not because it's going to, solve all the problems of the world. It's because we're just trying to push the human mind to places it hasn't been yet. It's really just trying to be at the forefront. At the end of the day, like I always tell my students, I spent like an entire year in graduate school studying the difference between a coffee cup and a donut. Like, what's the difference between a coffee cup and a donut? I mean, you could explain it physically, right? You could tell me about like its physical properties, but I'm saying mathematically, what's the difference? Well, I mean, how do we start to differentiate between, not differentiate like derivatives, sorry. How do we distinguish the two objects? Like, if you can't talk about physical attributes, like mathematically, what makes them similar? So you have to develop an entire branch of mathematics to do this. It's called topology. And you study this, right? Now, we only did it because we wanted to develop that subject and prove all these theorems. So it's almost like you start with this structure, and then from there you build. And you build this big thing called topology, and you just keep on asking questions and answering them. And maybe later on someone's going to use that, and that's what happens a lot in math. You'll have this one branch of mathematics that's trying to solve a problem, then they'll read some obscure paper on some other branch of math, and they say, oh, look, they're doing what we're trying to do right here, and they've already done it all. They have a proof. They have a theorem. I can use that theorem for my work. So a lot of times they're connected to each other, not intentionally. So it's just, you got to keep on asking the questions. You got to keep on trying to push and push. It's not for Any other reason, just that curiosity.
So what was the difference?
What's that?
What was the difference?
There is no difference between a coffee cup and a donut. I mean, there's not. Well, a coffee cup with a handle. If your coffee cup doesn't have a handle, then they would be different. It's the handle that makes it like the donut. I'm sorry. I mean, we've come this far. There's a donut, okay? And here's a coffee cup, right? I need to make that handle a little bit better. Okay, so this is a very loose explanation, all right? Imagine that I pick a point on this donut, and I draw a path, okay, on this donut that has to go back to that point, all right? So some path that lives on this donut, and whatever, it can go around that backside, and then it's got to come back to this. So this is just kind of on the outside edge, right? And if I do that on the cup, same thing, right? Now imagine that I start shrinking this path down, scaling it down, just shrinking it down. If I start shrinking that path down, is it ever going to cut through the cup? This path. Just imagine it's on the surface of this cup. Start shrinking down. Is it ever going to cut through the cup? No? Same thing with this one, right? What if the path that I drew went like this? Went inside the cup, down, came back up the backside, and then came back down, and then came up and through this edge. You see it? The path went in, down into the cup, back around, and then if I shrink that one, is it going to cut through the cup? That won't cut through the cup. It's just going to come back on the inside and come back up and eventually squeeze off and come back to that point. You either see this or you don't. Look, this last couple of minutes we're talking about topology right now. If you don't get it, I'm sorry. Okay? So look, now, so a lot of these objects are very similar in the aspect that if I do this in a lot of places, that's okay. Like I can shrink down. But if I pick this point and I draw the path that goes around, comes back around here, can I shrink that one? No, if I try and pull that string back in and shrink it down, I've got to cut through the donut. And I have the same thing happens on this handle. That there is a way that if I draw it around the handle and I try and pull it through, it's going to cut through the handle. In other words, you can deform this donut. Imagine it was like putty. You could deform it and turn it into this. Or you could deform that and turn it into a donut. And they would have the same topological properties. Now that's a very loose explanation of topology. In no way was that a lecture. All right, so I hope that addressed that. We are out of time. Let me see if there's anything else. I have 3 minutes. Derivative, higher order derivatives. We'll talk more about this. Velocity. Oh, remember? No, I didn't talk about this. This is not going to come up on the test, so you don't have to worry too much, but I'm going to say it because I have 2 minutes. I said earlier, if we have distance and time, right? That the derivative of this function f, the derivative would be its what? Instantaneous velocity, right? Instantaneous rate of change, but because it's distance over time, the derivative would be distance over time, which is velocity. Since we know that the derivative can be graphed, right? This would now represent a new function, which gives me the velocity with respect to time. So if you have a function that represents your position with respect to time, the first derivative is your velocity with respect to time. And now, if I take the derivative again, it's going to be velocity over time, right? Just like this one was distance over time was velocity. Now velocity over time is, in physics, what is that? Acceleration. This is acceleration over time. No, it's not going to be on the test, but you need to know this. You need to know that if you have position as a function of time, your first derivative will give you velocity, and your second derivative will give you acceleration. Always. All right, the test. We have, I'm going to tell you a little bit about it. My other class, I hadn't written the test yet. so I couldn't tell them, but they had all weekend to study. Yours is in, what, 46 hours or so? 16 questions, all right? 16 questions. There's problems where I give you a graph and I ask you to, talk about limits. There's problems where I give you some conditions and I ask you to draw. All right, so you need to understand the, continuity, and there is a continuity problem where you have to come up with that constant that patches the two functions together. Where I give you a piecewise function and patch it together.
I think that the old test you put online would be a good version for it.
The what?
The old test.
I haven't even looked at the old test. I couldn't tell you if an old test would be good or not. Yeah. What I did to make this test, all right, is I sat down, I opened up the book, I looked at the homework problems, I had my computer open, I was looking at the lecture problems that I did in class. That's really what I went off of, homework. This is going to be within the same level as the homework. If you've done your homework, you're good, but it's also conceptual. You still have to understand what you're doing here. It'll go all the way up through find f prime of x, okay, which is what we did today.
What are those things called again where you have to make it line up just right?
Well, that's the continuity section. That's the section on continuity, and there were two problems in the homework where you had to do it. One of them was really clean, the other one turned out to be a system of equations.
So we have one system of equations?
I'm not going to tell you I'm giving you, just saying, in the homework, that's what it was. So I would be prepared for that. If it comes, it comes. If it doesn't, it doesn't. All right, everyone. I'll be around tomorrow morning and Wednesday morning. Yeah, let me turn off my camera real quick.